All good with the QR code? I'll give you 5 more seconds to scan it. 5, 4, 3, 2, 1. Time's up. Okay. So let's look at the first one together. Once the treatment status is confirmed, it changes the potential outcomes that were initially conceptualized based on treatment levels. So this is related to what we discussed on Monday. I spent almost half an hour during the lecture to explain this. So let's see. This is indeed a false statement. Okay, remember, the potential outcomes, they're conceptualized even before the treatment status is confirmed. So something happens before cannot be affected by something happens afterward. Remember the example that we discussed on Monday? So my parents' expectation about my wage before I was even born, that basically formalized the potential outcomes. And that is even before they know my gender. Okay, when they're expecting me to arrive into this world, they'll be thinking about, oh, how much I'll be earning when I'm age 30 as a girl or as a boy. And then, once I'm born, my treatment status is confirmed, but that happens after the prediction. So causality, there is naturally a temporal order. It's always something happens afterwards, can be affected by something happens before. But what happens before cannot be affected by what happens later. So this is indeed a false statement. Now, let's look at the second one. If there is no selection bias, then the ATE and the ATT are guaranteed to be equal. Is this correct or false? Okay. If there is no selection bias, what does that really mean? No selection bias only implies that in the untreated state, the mean potential outcome for the treatment and the control group will be the same. But that only concerns one dimension of the treatment effect. Remember, treatment effect is about comparing the potential outcomes. It has to involve two states, both the untreated state and the treated state. So no selection bias does not guarantee that the ATE and the ATE will be the same. It only guarantees that the observed difference between groups is a reliable reflection of the ATT. So that's related to lecture 15. Okay? When there is no selection bias, basically that means in the untreated state, as indicated by the Y with the superscript 0, that the treatment and the control group, they have the same mean outcome, which is why the difference is 0. That gives a 0 selection bias. In that case, the last term, therefore the observed difference between group is the same as the ATT numerically. But for ATT to be the same as ATE, essentially we require that the treatment effect for the control group to be the same as the treatment effect for the treatment group. Knowing no selection bias, it's only about one dimension. Remember this table that we talked about? No selection bias only helps us to recover the values, while the average missing values for the untreated state outcome, but it doesn't tell us anything about this missing value and also this missing value for the control group. Therefore, we don't know whether the ATC will be the same as the ATT. And therefore, we would not know whether the ATT will be the same as ATE. Okay, the average treatment effect on the treated being the same as the average treatment effect in the population means no selection on returns. But no selection bias does not guarantee no selection on returns. They are related but distinct concepts. So be careful. No selection bias does not guarantee ATE and ATT will be the same. We need more conditions. And typically, no selection on returns are achieved under 3 scenarios. Either we have homogeneous treatment effects, so treatment effect is the same for every single individual in a population, that regardless of which subgroup we are looking at, the average effect must be the same since the value is the same for everyone. Or on top of that, not on top of that, or alternatively, we have equally distributed characteristics. So basically, that means the characteristics has the same or identical distribution in the treatment and the control group. They're equally determined. They have this, on average, the same education level, on average, the same age, on average, let's say, the same family background. Then this will imply no selection on returns. At the same time, will also imply no selection bias. Or we could also achieve no selection on returns. First of all, assuming no selection bias, that means we have the same untreated. Is it? Okay, yes. So that means the balance interaction effect implies the treated state outcome will be the same. Then given that we can control both the treated state outcome and the untreated state outcome, so we control both dimensions to deduce the treatment effect, then we will have no selection on returns. So a bottom line is no selection bias does not guarantee no selection on returns. So this is a false statement. Now, let's look at a third one, which is related to what we discussed on Monday as well. So in an RCT, the treatment is assigned in such a way that every participant has an equal chance of being included in either the treatment or control group. Is this correct or false? This is true, okay? Because essentially the key advantage of an RCT is randomization. By randomization, randomly assign individuals to treatment and a control group. Everyone has the same probability of being ended up in the treatment or the control group. So this is a correct statement. And it is because of this that we can balance the characteristics in the treatment and control group, thereby having no selection bias and at the same time, no selection on returns. So this is the third one. And the very last one. Randomization ensures that the average potential outcomes is the same across group. Is this correct or it's false? This is indeed a correct statement. So first of all, recall that randomization ensures that the treatment assignment is not affected by the potential outcomes. So basically, the treatment assignment is independent of the potential outcomes. Now, remember from this graph, we know that the potential outcomes, they happen before the treatment assignment. Therefore, the treatment assignment, it cannot affect the potential outcomes. And essentially, the RCT, the randomization, ensures that we don't have the effect going from the other direction. So RCT rules out that the potential outcome can affect your treatment assignment. Then given that there's no influence from both directions, essentially that implies they are independent, okay? So it's the potential outcome. It's the y naught I and y1 I that is independent of di. But the actual outcome is dependent on the treatment status, because the actual outcome, the one that we really observe, depends on the actual treatment status. So be careful with the wording here. It's the potential outcomes that are independent of the treatment assignment, but the actual observed outcome is dependent on the treatment assignment. Then, given that we have independence, that is basically the strongest form of no relationship, then when we compute the conditional expectation of the untreated state outcome, regardless of your conditioning on d being 0 or your conditioning on d being 1, they should be the same, because it should just equal to the unconditional given independence. Okay. So essentially, independence implies conditional mean independence. So knowing the treatment assignment doesn't tell us anything more about the potential outcome. Therefore, the best guess or the best knowledge we know about the potential outcome is just the average value of the potential outcome itself. And likewise, for the treated state outcome, this will be the same regardless of you are in the treatment or you are in the control group. So the average potential outcomes is the same across group, because it just doesn't depend on the treatment status. So this is a correct statement. So that's all related to what we covered on Monday and last Friday. Now, coming back to where we stopped on Monday. So we were talking about so in an RCT, random assignment ensures that there's no need to control for other variables for consistently estimating the treatment effect, because it ensures the treatment is independent of any other characteristics, pre-treatment characteristics. But we also mentioned that that doesn't imply having data on more variables is invaluable. There are two uses for control variables in the context of RCT, and one is about that can enhance the precision. And adding more variable basically comes with no price, because the variation in the denominator of the standard error is the same regardless of we included more control variables or not. So remember what we discussed in semester 1. So this is y, and we have that this is x1, and remember if x2 is also correlated with x1, then essentially the effect or the information that we're using in estimating the beta hat 1 is solely this clean part, okay? It's the part that is uncorrelated with the x2. But given random assignment, our x1 is uncorrelated with x2. So regardless of you add an extra x2 or not, the variation remains the same. Therefore, in the denominator, we always have the same value, regardless of it's a simple linear regression or multiple linear regression. But obviously, adding the x2 does decrease the variation in y that has not been explained by the model. Therefore, we'll have a better model fit, so a smaller standard error of the regression. Therefore, the standard error has a smaller numerator when we include more regressors. And as a whole, given that the denominator remains unchanged, but we have a smaller numerator, therefore the standard error will go down. So adding more controls will improve precision. So imagine in this we expand our causal model by adding more controls. And one bottom line here is, always you should only include pre-treatment variables. So remember, Monday we distinguish between two types of control. One is pre-treatment, or we call it predetermined random variables. Another type is what is called intermediate outcomes. Typically, these are post-treatment variables. And it's very hard to distinguish between intermediate outcomes and pre-treatment variables because we don't know which pre-treatment variables is actually not affected by the treatment. So a prudent approach is just to not include any post-treatment variables. Then these x that we include in our model equation should only be predetermined ones, so they're not affected by D. Why? So including only the pre-treatment variables ensures that we have a consistent OLS estimate. Imagine instead there is actually a post-treatment variable, so it's an interim outcome, which is the mid-year test score. And remember, our Y is the end-of-year test score. So the mid-year test score is an interim outcome. And we know that test score is essentially affected by innate ability. Innate ability is unobserved. There's no way we can include it in the model equation. Therefore, it's always in the error term. Now, innate ability is indeed independent of the treatment assignment D, given we have randomization. But innate ability is correlated with the interim outcome, the mid-year test score. But at the same time, this mid-year test score is affected by D. So if we look at our model equation, so if we look at the causal model, we have our end-of-year score, which is our Y. This is equal to phi naught plus phi 1b, which is the class size. And let's suppose we also included the mid-year score. Let's call this our x2. And we also have epsilon. Now, innate ability is in the epsilon. But epsilon is uncorrelated with D. So we know that the covariance between D and epsilon is 0. Now, the covariance between x2 and epsilon is different from 0 because your ability affects your test score. At the same time, the x2 is correlated with D. So remember back in topic 2, if we use an endogenous variable in the model equation, it will render the OLS estimates on all coefficients bias if those variables are also correlated with this endogenous variable. So although D is exogenous, but x2 is endogenous, and they are correlated, then by including x2, we'll make the beta hat 1 inconsistent as well, even though D itself is exogenous. This has something to do with the FWL theorem, remember. You really need to check back topic 2 if you're unfamiliar with this outcome. So using a post-treatment variable will induce inconsistency in our OLS estimate. Therefore, we should never include a post-treatment variable as a control. You should only use pre-treatment characteristics. Now, this is a problem of bad control. So either you go back and check the topic 2 lecture notes, or you read the lecture notes for RCT. There we have a very detailed explanation of why we'll have endogeneity by using post-treatment controls. So let's suppose we include more control variables in our analysis. So remember, we started from regressing the end-of-year test score on class size. Class size, it's the treatment. And gender, that is typically predetermined. And also free school meals eligibility, that is something predetermined, not related with class size. So if you look at the results from the simple linear regression and compare it with the one with the controls, so we can see that the estimated coefficient for a class size remains quite similar. It's only from 14.7 to roughly 14.06, so very, very minor change. But we can see at the same time the standard error reduces slightly from roughly 5 to 2.4. And in fact, the fact that we hardly see any change in the estimates of the coefficient on class size actually implies that we do have randomization at start, right? Because if gender and free school meals eligibility were correlated with the treatment assignment, then by including them, we should expect quite a substantial change on the estimated coefficient on class size. But here, we barely see a change. So that sort of confirms the initial random assignment. And therefore, there's no need to control for other variables, just if we are only interested or if we only care about consistency. So this is one of the use of control variables to improve precision. Now, another role of including control variables is that it allowed us to assess the efficacy of our randomization. So the whole idea of randomization is really to make the treatment and the control group comparable in the sense that the distribution of the characteristics are balanced. Now, the reason why we want to do randomization is because we want to recover the treatment effect. We know that simply looking at the observed difference between groups will not reveal the ATT because the observed difference between groups also captures the selection bias. Now, it's very hard to directly test that the selection bias is 0 because essentially the selection bias is unobserved because it involves a counterfactual term. We never observe the treated step. We never observe the untreated state outcome for the treatment group. So given randomization, we never know whether actually the randomization itself helps us eliminate the selection bias or not. Yes, randomization sounds perfect in theory, but how do we know whether randomization has been correctly implemented, whether we do have truly randomization in our study? Now, one way with additional controls is that it can help us to verify whether we do have randomization to some extent. So basically, this really exploits the fact that if we do have randomization, then our treatment assignment should be independent of all pretreatment characteristics. Then regressing our treatment assignment on pretreatment characteristics, we should not expect to see any significant results because they should not be correlated, given that they're independent. Or put it differently, the pretreatment characteristics should not help us to predict the treatment assignment. They should not be significant predictors. So one way we can test for or verify randomization is through what's called the balance test. We use the observed variables or the observed pretreatment variables to help us to assess the effectiveness of the randomization approach. So essentially what we want is a lack of correlation. As long as there's a lack of correlation, that gives us more confidence in that we have a randomization. So how do we do that? Essentially, this is the first regression or the first stage regression in the FWL theorem. Remember when we run the FWL theorem, when we use the FWL theorem to so when we run a model where we include the treatment assignment, our class size, plus beta 2 times the gender, plus beta 3 times the launch, and then plus an error term. I remember if we were interested in recovering an expression for beta hat 1, we can essentially use the FWL theorem, where this is the sample covariance between y and the tilde d over the tilde hat d over the sample variance of the tilde hat d, where this tilde hat d is actually coming from the regression of our d, our treatment assignment, on the gender and the launch. Okay, so essentially the balance test is just about the first stage of the FWL theorem, and we're testing whether the alpha hat 2 and the alpha hat 3, whether they are jointly insignificant at the same time. Well, what's more important is jointly insignificant, okay, but also we need to check whether they're individually significant or not. So we can see from the regression result, when we regress the class size on gender and free school meal eligibility, the t values are very small. Now, the small coefficients, it's typical because the class size itself is a binary random variable. It's either 0 or 1. So it's not that the small value of the estimated coefficients that tell us we have randomization, but actually it's the t value that matters more. So we can see that the individual t-test tells us that neither of gender or the launch eligibility is a statistically significant predictor for class size. And we can see that from the overall F statistic, we have very high p-value, 0.996. That basically strengthened the evidence of randomization. We failed to reject the null hypothesis of joint insignificance. So this basically confirms that at least in terms of observable characteristics, there is no systematic bias between the treatment and the control group. This can help us to sort of strengthen our confidence in one dimension. Of course, we might be worried about whether the unobserved characteristics are not balanced, but unobserved characteristics is never observed and never measurable. So to some extent, we'll just have to take it as it is, or you either critically assess whether we can safely believe that the unobserved characteristics are balanced based on the given context or the experimental setup. So this is the balance test. Now, coming to the very final point of RCTs. So if we do have genuine randomization, then that helps us review the ATT and ATE because we have balanced characteristics. So theoretically, RCT does not need assumptions because by randomization, we are in a perfect scenario. However, in practice, to ensure true randomization, that actually requires a lot of practical assumptions. And that's why typically it's very hard to see RCT in economic studies, and RCT is actually more relevant in science field. So typically, we would be concerned about two types of validity in RCTs. One is about internal validity. That relates to whether we think that what we have estimated from the sample is consistent for the treatment effect that we're interested in for this given population. So we would be worried about internal validity if there are uncontrollable differences between the treatment and the control group that affects the outcome. because in the end of the day, we want only one difference between treatment and a control group. It's just whether they are treated or not. We don't want any other differences apart from that. If there are differences apart from the treatment itself, then that will raise issue to the validity in our RCT. So some common threats here, basically, first of all, it's about whether we did use a good randomization techniques. And another one is about non-compliance with the protocol. So what non-compliance means is that suppose someone is assigned to the treatment group. They decided they did not follow the treatment assignment and instead went uncontrolled. Think about it in terms of maybe your group study project. Okay, imagine originally your lecturer assigned you to a group of 5 students, and then midway through the term, one student decided to withdraw from the group, but the lecturer didn't know that. And when they compute the average score, when they compute the score for your group, the lecturer also takes that student into account. Then, of course, the final grade for your group is not a genuine reflect of what your grade should have been. So this is the same issue here with non-compliance. So it could be that those who are assigned to a treatment group decided to go to control, or those assigned to the control group, they ended up getting the treatment. Then using the result, or then using the original treatment assignment to estimate the effect, we'll get an inconsistent estimates. And this could also be arise from small sample size, and typically that's always the case. Whenever we have a small sample size, that will reduce the power of your study. Or it could be due to some systematic attrition after randomization. So for example, some individuals, they decided to drop out after the treatment assignment, and that decision to drop out is actually related to the treatment assignment itself and the outcome. Then in this case, we have a systematic attrition, because once they drop out, those who remain in the study are no longer randomly assigned. There will be a systematic difference between those in the treatment or the control group. So suppose a group of students, they were originally assigned to small class. And these are the students who do really bad in exam. And at the same time, they hate being in a small class because they don't want to be closely monitored by their teacher. Okay, they decided to drop out. Then, even though originally we have random assignment, once those students drop out, those who remain in a small class is no longer the same in terms of their average characteristics compared to before. It's the original before the dropout, they were comparable with the control. But once those group of students drop out, they're no longer comparable with the control group. And therefore, we don't have randomization after these students drop out. So it's more about systematic attrition. It is the fact that the decision to drop out is related to the treatment assignment and the potential outcome that would render your RCT internally invalid. But if it's just random dropouts, let's say some students drop out just because maybe their parents have to move job or some exogenous reasons, then that wouldn't affect the internal validity. So that's another threat that could be posed in our consistent estimate. And the very last one is what is called the Hawthorne effect. So basically, the participants change their behavior not because of the treatment, but because they know that they're being studied. So for example, so the students assigned to the small class, they study harder or they get a better result not because of they are assigned to a smaller class, therefore they get better attention, but because that they know someone is actually watching their results. Then the outcome that we see is actually not because of that they're assigned to a small class, but because that they know they've been studied. So that is different from the causal effect that we intend to identify. So that will also pose threat to internal validity. Now, even if we hold internal validity, there's also external validity concern. Essentially, external validity is about whether we can generalize our finding from the study to the broader population or to a different settings. And typically, we will have threats to the generalization if we have non-representative samples, or that's, there might be a scale effect when we decided to make a very small study and apply it to the entire country. So I'll leave it to you to read these. They are all in the notes. Now, a properly executed RCT, it actually holds very high internal validity. So assuming true randomization, assuming perfect compliance, assuming a good sample size, assuming no systematic attrition, assuming no Hawthorne effect, the RCT is perfect for internal validity. It always gives us a consistent estimate of the treatment effect that we're interested in. But external validity is more important for policy evaluation. Okay, so high internal validity does not guarantee high external validity. There are two different considerations. So this is all about the RCT. Now, observational studies, which is the very last chapter of this topic. Hopefully, we'll be able to finish at least 3 or 4 more slides today. And then I think next Monday, we'll be able to finish on selection on observables, and we'll also start a little bit on selection on unobservables. Then by next Friday, we'll definitely be able to finish everything for topic 5. And we might even have some extra time left. And if we do, I might do a revision on hypothesis testing. Okay? So coming back to where we have started, I remember the reason why causal inference is hard is because it's essentially a missing data problem. There's always something missing. So for the treatment group, we never observed their results in the untreated state. For the control group, we never observed their results in the treated state. And that makes identifying the treatment effect difficult. And the whole idea of causal inference is about how we can solve this missing data problem. So essentially the idea that we want to do is we want to use, if we were interested in recovering ATT, then we want to use the outcomes from the control group, the observed untreated outcome from the control group, to approximate the counterfactual outcome of the treated group had they not been treated. Then this basically is about understanding the underlying treatment assignment mechanism. When will such an approximation be reliable or a sensible approach? And randomization is perfect because it basically balances all the characteristics and not only let us recover ATT, but also the ATE. However, RCT is typically invisible in a lot of contexts. And in those kind of situations, we would just have to deal with whatever observational data that we have in hand. Then how can we actually try to or attempt to recover the treatment effect we're interested in, given that there's no way we can manipulate the experimental setting, but we only have observed data? That the best we hope is that we can make the strengths of an RCT by ensuring that the treatment and the control group are as similar or as comparable as possible. So in these situations, it's very important to consider the inherent differences between the treatment and the control groups because we need to control for these inherent or systematic differences. So typically, there are 2 ways to address the selection bias, the difference between the treatment and control group in observational studies. So we either directly adjust for what is observable, and we will use indirect techniques for unobservable factors. So there is a whole lot of method out there within causal inference in dealing with these situations. Given the time constraint, I won't be able to cover all of them. I'll be only focusing on two. So one is about using the conditional independence assumption that help us to eliminate selection bias if the selection bias is related to observed characteristics. Or if the selection bias is related to unobserved characteristics, we can use a method called difference in differences, which is one of the most trending methods nowadays, at least in the last 5 years. And actually another way to handle selection on unobservables, already discussed in topic 3, instrumental variables. Okay, so that's also another approach that we can use in selection on observables, but we're not going to discuss this within this context. So coming back to the STAR data, and remember on Monday when I introduced the STAR data, I also told you that the teachers were also randomly assigned to the classes. Now, suppose we're interested in a question whether the teacher's experience improves the test score. And given that we know the teachers with different experience levels were randomly assigned to class, basically we can sort of set up a treatment assignment variable. So D is 1 if the years of experience is greater than or equal to 15 and 0 otherwise. And we propose to estimate D by regressing the test score on the treatment assignment. And we can see that here, so the roughly, 20 units, or 20 marks. Now, we have a question here. Do we really have random assignment? Just like we were worried about whether the class assignment was random, we are also worried about whether the teachers were actually randomly assigned to classes. So do we really have, in the causal model, all other determinants, whether they're observed or unobserved, are uncorrelated with the treatment assignment? Then, given what we've just discussed, we can use the balance test. We can regress our treatment assignment, the experience variable, on the gender and the lunch eligibility. Now we see a very different result compared to when we run this balance test for assignments. We see that the lunch variable is highly significant. It's minus 4.274, the t-value. And also the gender variable, although it's not significant at 5%, because it's smaller than 1.96 in absolute value, it's actually marginally significant at 10% because it's greater than the 1.645, the critical value for a two-sided 10% test. And we can see that the overall F-test strongly rejects the note of joint insignificance. Then basically the balance test tells us that the treatment assignment was actually not perfectly random. Now, why is this the case? So, in this experiment, the assignment of teachers were indeed random within school. However, the study cannot move the teachers across school, so there is non-random differences at the school level. And typically, we will expect variations in teacher experiences across schools. And typically, schools may be in the rural area because they have less opportunity to switch jobs. They tend to stay working in a inner city school than those because they have more opportunity to explore. They might tend to switch job more often, so they tend to have for example, less experience. Then in this case, those schools with more experienced teachers would tend to allocate these experienced teachers to students. So we do not have randomization at the school level, but we only have it within school. So suppose we were able to control for school characteristics by controlling for the location. So the city dummy is equal to 1 if the school is, or if the student attended a school in urban or inner city, and it's 0 if the student attended school that is in the rural or suburban area. Then if we now include the location dummy in our balance test, we can see that this location variable, the city, is actually highly significant. It strongly predicts the treatment assignment. The t value is -11. However, we can see that after controlling for the location, previously lunch were highly significant. Now it's statistically insignificant at any conventional levels. Okay, it's -0.81. The gender becomes marginally significant at 10%. But if we test the joint hypothesis that lambda 1 and lambda 2 are 0, we would fail to reject the F-test. The p-value is 0.129, which means we can reject regardless at 1 or 10 or 5%. Therefore, we do have evidence that once we control for school location, we have randomization, we have random assignment. But without controlling for the location, we do not have randomization. Okay, so this is the picture about selection on observables. Next Monday, we'll come back to the hardcore maths. So thanks for coming. Have a good weekend. And just to give you a heads up, there's quiz 4 in week 12, which is the week after next week. So there won't be pre-work. I'm not giving you any pre-work to do since it's already the last week of the term. I'm planning to make the test open on Tuesday, so give you a bit more time and flexibility on when to do it. But there will be no pre-work for quiz 4. And just before you go, about the very last teaching week, that Friday, should we go ahead with the lecture to do revision, or should we just cancel it? If you think we should go ahead, you can raise your hand. If you think we should cancel it, then, okay, so. Okay, then let's go ahead with it. Cool. I will send out an announcement next week to confirm the arrangements.